Hello, welcome to CLIP Chapter 2, Clip 1, and we have a lot to cover. I'm going to jump right into it. So the outline for this clip is about engineering survey, and the first topic I want to cover is this notion of need, know, how, solve. I know it sounds like you're kidding. That's all we got to do? Or what is that teaching me? First I want to encourage you to think that that is a very good thing to approach any problem. Problems in the book, problems in engineering, somehow boil down to those four words. And the first word is need. So what do we mean by need in this particular case? Need is the definition of the problem. It is what we're striving for. It's the thing that we're designing for. We need to know how to get a rocket ship to the moon, how to get a rocket to land a helicopter on Mars. And that has to be the first step in any engineering project, is to figure out what it is that you are doing. Sounds silly, but defining it accurately is going to help get a good answer. And then know. What do you know now? Mars is such and such a distance away. The atmosphere is thinner than it is on Earth, so obviously the helicopter is going to have a different design to it. And what do I know about that? Well, I have a certain amount of things that I do know. There are also things that I don't know. But collecting together in one place everything you do know is the very standard second step. And how do you know what you need to know about? Well, it meets the need. Are you ever going to revise all these things? Probably repeatedly. And then how? How am I going to solve this problem? How am I going to meet this need? Am I going to use Kirchhoff's current law? Am I going to use some kind of high-powered analytical software package? And am I going to fabricate it out of aluminum? I mean, the kind of choices that are in front of you, you have to start answering those. How are we going to meet this need? And then solve. And the solve is the carry-out. So this could be applied to an engineering design problem. It could easily be applied to an engineering problem in the text, or that I give you on an exam. And if you channel your thinking along those lines, you won't spend time flailing around having realized, oh, there's something I need to know and I didn't collect that, or there's something that I don't know and I need to take that out of the design altogether. So need, know, how, solve is a really great, handy way to apply things. Now I'm going to start talking about the tools and things that we need, the basics in all fields of engineering. Basic tools that are going to be required. And we have this nice book, and one of the things that engineers do all the time is make drawings. You can make formal engineering drawings or sketches or something in between, but most engineering problems require a drawing. Writing a software program very frequently requires making a flow diagram. So you make diagrams, drawings of the right side, the left side, the top, the bottom, and so on. And it's just a word or two about the kinds of drawings that we have. This is an isometric drawing. So it's the object drawn at an angle with respect to the piece of paper that appears on, so that you can kind of get the three-dimensionality of it all at once. Then the next type I'm going to show you is, well, there's some more isometric drawings of various and sundry objects, but at the bottom here is the orthographic projection. What does that mean? Well, here's the object, so in isometric view, so you can get a sense for its what it looks like. But if we want to tell the machinist, make this shelf such and such a distance and so on and so forth, to actually fabricate the thing, it turns out to be super handy and constantly done to have a top view, as if you're straight overhead and you draw it out, and a front view. Well, this front view is not there for no reason. It's there because this dimension here, left to right on the top view, is the same as the left to right dimension on the front view, and the side view is, of course, this side, but its height is aligned with the height here. So you get used to reading these orthographic projections, and they're a very good way of drawing an object. And scale and dimensions. These are the dimension lines. It's a little extension from the actual object. It's drawn here in the isometric view, and you can see that this distance here is supposed to be some number, and this another number, and this another number. And it's common that you don't put down every number. For example, once you know the width from left to right here, and then we go to the back, if it's assuming that these are 90-degree angles, then once we have that dimension, we don't need to separately write down that dimension, because we just take this number and subtract it from that number. And typically that's being done with computer-aided design, rather than in the early days, long ago, with a T-square and right triangle. And anyway, I admit I used to draw those things with those. And here's like an exploded view, and there's all kinds of different ways to make views of things, and you can make a little sketch on the back of a napkin if you have to get yourself started, and eventually turn it into a bona fide engineering drawing. And I will scan down through there. Now back to the outline at this point. So drawings, sketches and formal drawings, you saw some of those. Measurements are required. Measurements of all sorts of things: the height, the width, the weight, the density, the number of ohms in a resistor, and so on. And virtually always, I can't think of a case that it doesn't happen like this, you need two things in the measurement. You need the amount, that is the numerical value, 10, and the unit, in this case, miles. There's a big difference between 10 miles and 10 microns. You have to get the number right, and you have to say what the unit is and what kind of, let's talk about units for a minute. It's a fantastic thing of, I don't understand, it's a philosophical issue in my thinking, that there are only 6 fundamental units. That's it. There's only 6. Let's see if I can get to those. I'm sure I can. And I think I went by them. And there they are for the SI system. Now there are various systems of units, but they all have only 6 fundamental units. I won't tell you about the other ones, but MKS is one, meter kilogram second. This is SI, which stands for Système International, some French term. So we have the meter, that's length. The second, that's time. The kilogram, that's mass. The degree Kelvin, that's temperature. The mole, that's the number of atoms or molecules. And the ampere, that's the measure of electric current. All other units in the SI system are derived from these and can be broken down to be expressed just as these. Let me say something about that as we're looking at it. Let me actually flip over to the other thing, and I don't have to keep taking myself in and out here. We'll use SI. Most people are using SI. And the conventions, there's some conventions in using these units. One of them is that important one. If the unit is named after a person, for example, volt is named after volta, ampere is named after ampere, second is not named after a person. So if it's named after a person, then its abbreviation is capitalized, and also by convention, behind the number, which represents the number of amperes, we would see amperes in parentheses. Not always followed, but certainly in scientific papers it is. Here is another example of abbreviation kilogram, and that's not named after a person, so it's lowercase. Now, numbers, the size of the numbers. It's possible to have something be 0.000001237. Wow. 137 is important. All those zeros are going to drive you crazy. And so it's nice to have a prefix that tells you what magnitude, and I'm sure it's not the first time you've heard of this, but what magnitude of a number, so that the actual number you're looking at is a small number with several digits and not with a whole bunch of zeros either in front or behind it. So that's why we end up having to use, and you need to just learn them, and there's no particular there's some logic in them, but it's basically something that you have to learn. And it's coming up momentarily, I do believe. Though, yes, it is. It's right down here. So here are some of, not all of, the prefixes, and they mean a number times this factor. They're mostly factors of 10, of 1,000, I mean. Sometimes there's a factor of 100. I never use those. I only use the ones that are a factor of 1,000. So if we start with a number that's, like deca and hecto, I've never used that. I've never even seen it used. Kilo, like kilogram, means 1,000 grams. Megagram, I never heard of a megagram. Nobody ever says megagram, but they say mega ohm or megavolt. Mega ampere, gigabyte, that's a billion. Terabyte, that's a 10 to the 12th. So each of these, and then on the small side we have another set going in the other direction, and I never use deci or centi, yes, centimeter. That's the only place I ever use centi. But basically we go from meter to millimeter to micron, nanometer, picometer, femtometer, atometer. Give me a break. Probably not in meters, but in seconds, yeah. The size of an atom is on the order of a nanometer, so things that are a lot smaller than that are starting to not matter. We can't see them anyway. But a picoampere is possible, and a picofarad, and so on. So those prefixes will save us a lot of time, and unless you know them, you're going to get lost in a hurry. So please take a look at those, or have it handy. Mark the book, write it on a piece of paper, so that you're not getting lost in that. Next topic is about the significant figures in the numbers. We have just talked about the prefixes. Look in the text. And for significant figures, what do I mean? What I mean by this is, if you go out and measure the length of a road, and it measures out to 1,200 yards, and that's, you only have the two digits, the 1 and the 2, and then you measure some time with great accuracy, say 100.1857 seconds, that's not unreasonable. You could measure that. But now if you start figuring out the velocity by taking the distance and measuring and dividing by the time, you're going to get an answer which may have many digits, but most of them don't matter because you only know the distance with an accuracy of 2 digits. So that becomes your significant figures. Whichever measurement or number that you have that is the least accurate should set the answer. Now, you can carry the calculation with lots of numbers. Who cares? It's a computer. You can carry the numbers. But when you get done and you report the answer, do not report an answer which has more significant figures than the worst number you're working with, because it will mislead you and everybody else. So you can read through that in the text too. Let's talk a moment about computations. Engineering involves a lot of computations. Think of the computations that have to be done to get a rocket to Mars and land it on the surface without crashing, and it's unbelievable. I mean, I look up at Mars every night and I'm amazed that we've sent objects up there, and I think in due course we'll send humans up there. And looking at the moon, it looks close by comparison. But it's not an easy thing to do, and it involves a lot of calculations and computations. So how are we going to carry those out? I can tell you how. It's easy to know how. I will go to this, and I will go to my little outline. And we're going to use computers, right? Computers. This thing that I jokingly call not the ones at the bottom, but the one at the top, the so-called smartphone, is only barely a phone. I mean, less than 1% of what that thing does is a phone. It browses the internet. It has this calculator built in. It's a communication device, and it's a computer. It's a pocket computer. But who but some kind of nerdy person would want to say, oh, I have a new pocket computer? No way. So we'll call it a cell phone, and a smartphone rather, and that'll relieve you of being the village nerd, in the bad sense of nerd. So we're going to use computers to do our calculation. And when we're using a computer, we've got two different sides of it to think about. One is the hardware itself. What is the size of the microprocessor? How much memory does it have? Physically, what is it composed of? It's hardware. Better hardware, maybe it's faster, has more memory, and can be more capable. It might be a personal computer, a big parallel. It could be something out on Amazon Web Services. I've done that. I have an account where I can program 512 computers. There's no way I'd ever put the 512 computers in my home. I couldn't afford it, and the electric bill would kill me. So that's a cloud solution. But for a personal solution on your desk, tablets even, and smartphones. Now, computers don't do anything unless they have a program that tells it what to do. This is the software. And don't get caught in that trap and that idea of thinking that, oh, computer advancements in computing are mainly driven by the hardware. Incidentally, we'll get to it, but there's a thing called a graphical processing unit, GPU, which was started out as a graphics thing and is turning out to be a compute thing, and it's like totally changing computing. So computer programs run on that hardware, and what program are you going to use? And I'm going to use in this class, and I use almost always MATLAB, because it's, I think, the best language of scientific computing. I'll have a little lecture on MATLAB as we get going. But when you have a bunch of numbers and you have to make graphs and pictures and everything, in the general way, you would use MATLAB. But for more specialized things, you can use PSpice, for example. And one thing that popped into my mind just now while I'm talking is AutoCAD. It's a drawing program. And MATLAB can solve physics problems, math problems, financial problems, biology problems. It's designed to work on almost any kind of problem. But maybe it's not as good, and it actually isn't made to make drawings. So there is a special purpose program for drawing called AutoCAD, and there's another one called SolidWorks, and there's various purpose-built pieces of software out there. PSpice is another example that's out there. And let's see, I already mentioned the Amazon Web Services. I've got a couple of links there that you could go to. Maybe I'll put them in a document a little more easily obtainable by you, but you have to type them out by hand right now. And the National Algorithms Group, I went by without mentioning. This software, it's not just the software. It's not like there's a new version of a software program. It's that there are algorithms that run in software. And the algorithms are being developed by a massive consortium called the National Algorithms Group, and the things that they're doing is advancing computing like crazy. It's not well known. A lot of people in engineering don't know about this because it's kind of new. And so Amazon Web Services, this massive computer that they have, and the one that I told you I can run 512 different computers. Well, they're in a node, but I can run them. And that's a fantastic power. I can do a problem that would take 500 minutes, let's say on the order of 10 hours, I can do in 1 minute. That's worth it. That's important. So let's summarize what got discussed here. I started out with the very important idea of solving any engineering problem before you even get to started. Your steps to getting it done is need, know, how, solve. And as you use it more and more, you'll do it without thinking those 4 words. You'll just naturally do that to solve problems. But when you're approaching a new problem, not a bad idea to jump to that. There's engineering drawings. They're important. We just talked about orthographic and orthogonal projections. Measurements are required. The projection is orthogonal. And the measurements are required in engineering, and we need to know an amount and a unit. And there's only 6 fundamental units. The rest of them are derived. Wow, that's like a miracle of the universe somehow, in my thinking. There are a very large number of those derived ones. Our conventions I mentioned. There's prefixes. There's nothing for those prefixes except to just memorize them. If you put them on a piece of paper, if you don't know them already, or put it handy, that's a good way. And computations. Engineering are doing all these things. Computations, we're talking about hardware on the one, and we're talking about the software that runs on the hardware. And you can expect both of those to continue to advance at a rapid pace for, I think, decades at least. Maybe for your entire career. No one really sees it ending. I like MATLAB for the software. I will teach you MATLAB. I will teach you parts of MATLAB. And let's see. There are written programs to do drawings or to solve electronic simulations. PSpice's electronic simulations. Don't forget the cloud. The cloud is going to make a huge difference, and I think a lot of things in engineering are going to rely more and more on the cloud. I hope you learned a lot. I enjoyed doing my best. I want to make this as easy as possible to soak into your brain and help you become an engineer and get a great job with a good paycheck and do interesting work. That would make me happy. I salute you.